So average means, you know that, so if I want to find the average potential energy, so I told you the potential energy when time t is equal to 0, right? So the potential energy will go something like this. The kinetic energy will go something like this. If I plot the average for the yellow line, right? So you may be getting some average somewhere here. So the average potential energy is equal to, what should I do? I should add all this entire area, and then I have to divide by the time, right? So what do you do to find the average between 5 subjects? Add all the values, add all the marks in the 5 subjects and divide by 5. Similarly, I have to add this, I have to integrate this curve, meaning it's the area under this curve. And then I have to divide by this distance, this time. So when I do that, I'll be able to get the average. And what do you mean by average? Instead of changing values, I want to have an average, which is a constant value. So it will be something like a straight line. So if I say that you got different marks in different subjects, say 60 in one subject, 85 in another subject, 75 in another subject, 95 in another subject, maybe 80 in another subject, something like this. Okay. So if I calculate the average, let's say it's somewhere around, say, 82 or 83, I don't know. Okay. So what it means is it's similar to having the same constant value in all the 5 subjects. So that's the meaning of average, right? Again, I do not know the average here. You can calculate it yourself. But what is the meaning? It's the same thing like, having the same values in all the 5 subjects. So that's what I'm trying to say here. So it's same thing, if you have a curve like this, the average is something like a straight line. So the area under this red line should be equal to the area under the yellow line. So that's the idea. If I do the total here and if I do the total here, I should get the same value. That's the meaning of average. So take it down. So very often you'll be using this concept. So take down this concept properly. So how do I get this height? Area is length into breadth. So this is your length and this is your breadth, L into B. Okay, so this is nothing but your time. So if I find the total area, L into B is equal to total area. And if I want to find the height, this height, then I have to divide by the L or the time T. T is the time period, okay, for one full cycle. Okay. So you add all the subject values and then divide by the number of subjects. So similarly, I'm adding or integrating entire curve to find the area and then divide by the time period. That will give me this height. That's all I'm saying. Half. This is a long integration. So integration process. So K is equal to M omega square y squared. Y is equal to A sine omega t the whole square divided by t, but don't forget there is integration. Mass is constant, omega is constant, amplitude is constant, so I have to integrate only this term. Okay. So I don't want to confuse you right now. Okay, so when you integrate this, what you will get is I'll be getting because you will be studying integration only in your 12th standard. Okay, so when you integrate sine squared omega t, what will happen is sine squared can be written as cos 2 theta is equal to 1 minus 2 sine squared theta. So sine squared, this can be written as 1 minus cos 2 omega t divided by 2. So this is called the integrable form. Okay, even 12th standard students will have difficulty, so I don't want to confuse you. So if I integrate these things, I'm going to give you only the final answer. So when you integrate this, I'll be getting 1 by 2 m omega squared a squared. Meaning it will be 1 by 4 m omega squared a squared. Similarly, for kinetic energy also, the same thing will happen. So take down these methods. Maybe if it's there in your textbook, you can study it, okay? But it will be useful for your numericals. So that's why I've given this. This we derived it in the last class, so you should remember this. So these m and omega square are constants, so I'm keeping it outside. So integral of a squared minus y squared. Again, this y can be replaced with a sine omega t. So again, I can take the a squared commonly out. So I will be getting very similar to this one, half m omega squared a squared. And then 1 minus sine squared omega t will become cos squared omega t. So integral of cos squared omega t divided by t will again become 1 by 2. So for now, I'm not going to do that integration, okay, because they're not going to ask you the integration method. We'll be getting 1 by 2 into 1 by 2 m omega squared a squared. What this means is 1 by 4 m omega squared a squared, 1 by 4 m omega squared a squared, which means if I add it, it will become 1 by 2 m omega squared a squared. That's what we studied in the last class. So if you calculate the total energy we calculated it as half m omega squared a squared. Okay, so for now, don't worry about this integration methods, okay, because after studying at 12th standard, this will make more sense. So finally, we'll get something on this. Okay, there is something called damped oscillations and undamped oscillation. So undamped oscillation is going to look something like this. Amplitude remains same all the time. So even after passage of time, amplitude does not change. But most of the oscillations which we come across in our usual day-to-day life is damped oscillation. So you just oscillate a pendulum, what will happen? It's not going to keep on going forever. Initially the amplitude is higher and then the amplitude decreases and it decreases and it decreases. So it means the amplitude decreases in a exponential way. So very important. So take it down. So the amplitude decreases so quickly. Here amplitude remains the same. What is your x-axis? This is t. What is your y-axis? Displacement. So this is called damped oscillation. This is called undamped oscillation. So let's say a child is sitting in the swing and you are pushing it, you're standing behind and pushing it. So the swing, eventually it's going to stop, right? But the child wants to keep on going. That means somebody has to stand in the back and they have to keep on pushing. So if I want to keep the amplitude the same, somebody has to keep on pushing. Then only then this is possible. So this can be possible only by forced oscillation. So take it down. There is a lot of theory given in your textbook, but they also say that it is, the derivation is not given properly. Okay, a lot of steps will be skipped because you need little more higher level mathematics, which is not available for you right now. Okay. Imagine that I have a spring. I have mass here. So as I oscillate this, right, as I make it oscillate, right, what will happen? You have studied that f of the spring is equal to minus kx. So k is the spring constant, y minus. If I pull it this way, the spring is going to pull it this way. If I push it this way, the spring is going to push it downwards. So that means spring force is always opposite to the extension. X is your extension, which you studied in your 6th chapter, work power energy. What is S? Spring force. Remember, suppose if I take it to space, or maybe if I evacuate this chamber, right? Initially, you have some air, for example. Okay. If I make it oscillate inside a bucket of water, right? Will it die down quickly or will it keep oscillating for a longer time? What do you think? Anybody? Please open your mouth. I don't know if I'm talking to myself or if there are some students there. Instead of oscillating in the air, if I take it inside a bucket of water, will it oscillate easily or will it stop very quickly?
It will stop quickly.
Stop quickly.
Very quickly. Why? Why? Because the mass is running against the water resistance. And in the air, it is running against the air resistance. But in vacuum, right? Suppose if I evacuate it, then there is no fluid to oppose the motion, which means it will be going for a longer time. You don't following what I'm saying? Okay, so that means
Yes, sir.
depending upon the fluid which you have in the surrounding the mass, right, the damping will be more. So when you're going at say 60 km per hour in your two-wheeler, right, you are going to face more air. But suppose if you are going in vacuum, right, then obviously there is no air, which means you can go even more faster, okay, because the air resistance will be completely removed. So that means when I'm let's say this is my bicycle or two-wheeler, right? When I'm driving this way, my air resistance is this way. So this is your driving direction. Remember, I'm not talking about the wind velocity. Okay, sometimes what will happen is there'll be some wind. So I'm not talking about the wind. Imagine that the entire air is kind of stationary. In spite of that, even though the air is stationary, when I am driving very fast, right, I will feel lot of air resistance. But suppose if I am going in the opposite direction, then the air resistance will be this way. Again, I'll be facing lot of air on my face. Okay, so that means whatever direction which you are going, the air resistance is going to be opposite. Just like this spring. Okay, when I pull it down, the spring is going to pull it back upwards. When I push it upwards, it's going to push it downwards. That means we put a minus here. What is V? V is the velocity. So when you're going at 20 km per hour, you don't feel that much of a air resistance. When you're going at 60 km per hour or 80 or 100, as the speed increases, what do you observe? You will be feeling more and more air resistance, right? So it means the damping force is proportional to the velocity. Is that fine? Everyone following this? So these all things which you are experiencing in day-to-day life. Okay, so you have to connect that with your physics here. So this damping force is proportional to the velocity. Whenever we have proportionality, we bring in a proportionality constant, and that constant happens to be B. So we call it as a damping constant. This is spring constant, right? So force or spring constant. This is damping constant. So that means even though if I'm driving at the same speed, instead of driving in air, suppose if I was driving in water, inside water, right? Then the damping constant will be higher. So the damping force by water will be much higher. So far I have given you two equations. One is due to the spring force, the other one is due to the dampening happening in the fluid. Most important formula in mechanics is sigma F is equal to ma. So sigma F means I have to add both the forces, Fs plus damping force So this can be written as minus kx. This can be written as minus bv is equal to ma. So listen carefully. X is extension, right? Velocity is also a function of time. Acceleration is also a function of time. I think let's see if x is a function of time. Well, as time progresses, that is extension will also change. Okay, we can say x is also a function of time. Okay. That means what I'm seeing here is displacement, with respect to time, the displacement will change. With respect to displacement, the velocity will change. With respect to displacement, the acceleration will change, or with respect to time, the acceleration will also change. So x is a function of time. Velocity is also a function of time. Acceleration is also a function of time. So in your mathematics, you must have studied f of x. What does that mean? F of x is equal to x squared plus 5x, something like this. So as x changes, the f of x value will also change. So as time changes, the x value will change. As time changes, velocity will change. And as time changes, acceleration will change. Velocity is nothing but dx by dt. If I bring these minuses on this side, it will become plus. So that means I can write it as m d squared x by dt square. All these things are there in your textbook. Okay, so you have to study it for some purpose. If I bring everything on this side, the other side is going to be 0. This is what we call it as differential equation. X squared plus 5x is a algebraic equation. So similarly, this is called differential equation. Yeah. So just like algebraic equation can be solved to find the x value, I can solve differential equation also using some methods which has not been introduced for you. Okay. So solving the differential equation. So when I say solving a quadratic equation, right, what do? You find the value for x. Similarly, when you solve for this, right, we try to find the value for x here. Of course, as I told you, x is a function of time. So for now, you just have to remember this equation, okay, because in the textbook itself, they are not given the method. So as I told you, this is a solving method which you will be studying only in college level. Okay, but the purpose of the text here is to show you that there is something called damped oscillation, and you can get an equation for damped oscillation. Okay, when you are going in a car, right? When the car is going across a speed breaker or a pothole, what happens? You feel the vibration. So it means there is going to be a vibration, and that those kind of vibrations has to be studied. So in every mechanical engineering situation, right, all these things will be studied. As a design engineer, you have to do some simulations, and you have to find out, what is the best situation. So that's why you're studying all these things. As I told you at the very beginning, amplitude is not a constant. So as time progresses, the amplitude keeps changing. Maybe it's 5 centimeter here, 4 centimeter here, 3 centimeter here, 2 centimeters. So it keeps decreasing very quickly. So take it down. Amplitude is also a function of time. Okay, wait a minute. I think I made a mistake here. So I'm talking about this entire term, right? So you see, whatever is in front of sine or cos, that is my amplitude. Okay, so it's not just this one, the entire thing. So as you can see, it's a function of time. And that's what I was showing you in the, you see, it's an exponential decay curve. So what do you mean by exponential decay curve? So with respect to time, the value will keep on decreasing very quickly. Okay. So exponential drop or exponential decay. What do I mean by that? As t value changes, the amplitude is also going to change. Amplitude decreases drastically. But drastically is English word. So the mathematical equivalent will be here exponential decay. Omega dash a by m minus b by 2m, the whole square. So what this means is, to listen carefully, as the damping constant increases, right, this value will get smaller and smaller. So that means as it progresses, the amplitude, the angular frequency omega dash will also change. So what do you mean by that? So initially, let's say if you had a frequency like this, as because of the amplitude, right? So let's say this is the original situation. So which means based on omega, right? Based on omega, I can calculate the time period. But what if it changes to this? What happened? The time period increased. So that means when this value increases, this value will decrease. You know that omega is equal to 2 pi by t. That means if omega decreases, time period t is equal to 2 pi by omega. So if omega value decreases, the T value will increase. Meaning if you are putting it inside a bucket of water, the spring is going to have a higher time period. Okay, because it's moving very slowly. If it's moving very slowly, it takes more time to complete a oscillation. That is what we mean by time period increasing. Bit confusing. Okay, so don't worry about it. A special case here would be when there is no damping constant. And there is no damping medium, right? What does that mean? B becomes 0. When B becomes 0, the omega dash will become square root of k by m. But I told you omega is nothing but square root of k by m, which means it's matching with the omega. Which means the frequency will remain the same. And when I say B is equal to 0, what does that mean? This becomes 0. Anything to the power 0 is 1, which means the amplitude remains the same. So take it down. So there is no such thing as minus 0, right? So either it is minus 1 plus 1 is there, minus 2 plus 2 is there, but 0 is, you cannot put any plus or minus here, right? So even though there is a minus in the formula, so anything to the power 0 will become 1. Which means amplitude remains the same. What does that mean? When there is no damping force, right? Which means it will keep on oscillating. So suppose if I evacuate the chamber and if I put the spring inside, it will keep on going, theoretically speaking. So if I say the amplitude is same and the frequency remains the same, it means it must be a undamped oscillation. So undamped oscillation is a special case of the damped oscillation. Undamped, but then you are not giving any extra force, no external force. So make a note, we'll talk about this later. Definitely not an easy one. Okay. So in the textbook itself, they are given it in a very, very disconnected way. So as I told you, the first thing you have to understand is there is something called spring force and damping force. So you are adding them and then you are doing this mathematics. Okay. This is what is called differential equation. When you solve it, right, they didn't give you the method because it comes in college level mathematics. So when you solve it, you will be able to get an equation something like this. What this means is the amplitude is a function of time. And omega dash is kind of getting something like this. So a special case is when D is equal to 0, there is no damping medium, which means omega dash will become square root of k by m, which is equal to omega. And the amplitude will become anything to the power 0 is equal to 1, which means into A, which means the amplitude remains the same. Everyone clear? Anything not clear, please ask me. Are able to follow at least 50%? I'm sure it's not going to make 100% sense right now. Okay. So when you sit in the class, I expect you to understand at least 50-60%. And then as you keep on reading the textbook, as you go through the notes, class notes, handbook, eventually your understanding will slowly improve. Yes, no, understood, not understood.
Understood, sir.
Okay. Okay, very good. That's what is given in your handbook here. Okay, I may have given you some extra steps, so I keep on telling you take the notes properly. We are going to follow the same methodology for forced oscillation. Only thing in forced oscillation, in addition to the spring force and the damping force, you will be giving a positive force. Where did this positive force come from? When the child is sitting in the swing, you are going in and standing in the back and you keep on pushing it. Okay, so that means that is a positive force. Again, it's going to be the same thing. Okay, I'm not going to repeat this. So okay, I'll get some water. Just a sec. You see, the spring force and the damping force are the same. Only thing, now you are standing behind the swing and you are pushing the swing, which means that is your extra force, positive force. So these things are opposing the swing action, and this is adding to the swing action. You are giving it in the positive direction. So that's why this is minus against it, and this is positive. Again, most important formula in mechanics is sigma f is equal to ma. So if I keep f of t on one side and if I keep the other things on the other side, m mass into acceleration plus b into velocity plus k into x is equal to the force. But what is acceleration? D squared x by dt square. What is velocity? Dx by dt. What is x? X is your displacement. What is force? Maybe you are giving it in a, instead of giving a constant force, let's say you are giving a driving force like this. So with respect to time, you keep on changing. Solving this differential equation, right? You'll be getting x of t is equal to a dash cos omega t omega d into t plus 5. Again, as I said, you don't have to worry about this, but you may have to remember this, okay, depending upon your school exams. You will get a lot of questions in this for your NEET and JEE and other entrance exams. So a child is sitting here just like a pendulum, right? You know that the pendulum has got a natural frequency, right? Suppose if I'm standing here and if I keep on pushing the pendulum at a particular point, just like the swing has been Swing is being pushed by the person who is standing behind. Right? So you keep on pushing so that the swing keeps on going. So you know that there is something called natural frequency of the pendulum or natural frequency of the system, like a swing. Okay. So that natural frequency should match with your frequency. Only if that frequency is matching, then it will have the maximum amplitude. Okay. What do you call that? When the driving frequency matches the natural frequency, what do you call that phenomenon? Didn't we talk about resonance anywhere? So take it down. And the driving frequency omega d matches with the natural frequency, right? Then what will happen is resonance will happen, meaning the amplitude will be maximum. This maximum, meaning the energy is maximum in this situation. So the energy given to the system will be maximum. So take it down properly. So since we are talking about forced oscillation, the frequency of pushing should match with the frequency of the natural frequency of the system. Only then the amplitude will be maximum. You see, it looks like a very complicated equation. Amplitude A dash is equal to F naught divided by root of m squared omega squared minus omega d the whole square. Sorry, omega d square, then the whole square plus omega d square to b square. Okay, now how do you get this? You know, we don't have a proof right now, so we have to take it without proof. But you'll have to study the special cases. So when the damping is 0, right, what will happen? When b is equal to 0, this entire term will go away. Okay. So what is left is only this one. So in that case, what will happen is amplitude A dash will become F naught divided by square root and squares will cancel. So what is left is m omega squared minus omega d the whole omega d squared. So that's a special case. So take it as special case. Another special case might be the resonance. In resonance, what did I say? The frequency is matching with the driving frequency is matching with the natural frequency. So if this is the case, what will happen is this term and this term will cancel. Okay, so what is remaining is only m, so not by m. And what did I say in resonance? The amplitude will be maximum, right? So f naught divided by this term and this term will cancel out. Okay, which means I'll be getting m. So if this value is a small value, this value is going to be bigger. Okay. Suppose if you had a value here. Okay, wait a minute. I think I'm making a mistake here. This will become 0, right? So it means amplitude, yeah, I'm right. So when I say this is almost close to 0, right? What will happen is the amplitude will go to infinity. So the amplitude is very high. In mathematics, you call it as limiting case. So as this gets smaller and smaller, this will get bigger and bigger. Any questions? Only the special cases, they may ask you some questions. Okay, so you have to remember these formulas. In the handbook, whatever things you have to remember, I have given it neatly in the box. So as I told you, whatever we discussed so far in this, it is okay, no issues. Okay, it is there in your textbook. This is also there in the textbook. Okay, but then you don't have, there are some disconnected steps. You don't have a continuous thing because of the solving methods. Phi is also given by tan phi is equal to V naught by omega d x naught. Okay, so I don't think these things are discussed in your textbook. Pendulum is discussed, I think. Bowl probably it's discussed. I think this is also discussed, these two things. These things are coming in your next year. Okay. But only if you know the basics from this chapter, you'll be able to apply it in the 12th standard. Okay, this is also 12th standard stuff. Okay, so some of the things alone I'm going to discuss. 1, 2, 3, 4. So only 4 things I'm going to discuss. All the other things, if you are studying for entrance exams, you can come back and refer to this. Okay. So the first one is very easy, the simple pendulum. So only when you ask questions, you will learn more. So please try to understand it properly. So this I'm going to take this L. This I'm going to take this theta. So if this is theta, mg is going to be acting downwards. I can resolve this into two components, two forces. So if this is theta, this is also theta. This is theta, then this is adjacent side, so mg cos theta. This is mg sin theta. So you see, this is something like a circular motion, part of a circular motion. So which means we'll be taking this restoring torque. Somewhere in your seventh chapter, we studied torque is equal to I alpha. Why? Because F is equal to ma. Similarly, this is linear world. In the rotational world, I told you torque is equal to I into alpha. Just side note. Torque is nothing but force into distance, right? Perpendicular distance. So that means forces mg sin theta is what is pushing this way, and then it's the length. So you see this theta is positive, but the force is negative, right? So which means we put a minus here. When the theta is on the positive side, the force is on negative side. When the theta is on the negative side, the force will be on the positive side. Somewhere you studied that moment of inertia for the mass m is mr squared. Why? Because this is the mass and it is going around a circle, the radius L. So that means I'm going to write as ml squared. Means moment of inertia will be written as ml squared into alpha minus mg sin theta. Sin theta I'm going to write as theta. Why? Because in mathematics very often we'll be taking this. When theta is small, sin theta can be approximated as theta. So take it down, which means sin theta will be written as theta. What does this mean? This is very similar to acceleration is equal to minus omega squared into displacement y. Okay. Here it is linear displacement, linear acceleration. Here it is rotational angular acceleration. This is angular displacement. which means according to this equation, in place of omega squared, I have G by L. So omega is equal to root of G by L. And that's why so this is a formula you might have used it in somewhere you must have seen it. Have you seen this formula anywhere else? Did you do some simple pendulum experiments in your lower classes?
No, sir.
No? Okay. So what this means is as the length increases, the time period will also increase. Suppose if I keep a tabletop pendulum like this, if I keep oscillating back and forth like this, and suppose if I go to the ceiling hook, suppose if I make a very long pendulum here, right? So what will happen is this will keep going for a longer time. So the time period here will be less. Why large? Because it will take more time to finish this oscillation. So that means as L increases, the time period will also increase. Any questions, anybody? So any step which is not making sense, please ask your doubts. I can zoom out. So any steps which is not making sense, please ask. So what we have done is we have derived the omega for a simple pendulum and we have found the time period for a simple pendulum. If they ask you the frequency will be 1 by t. So 1 by t will be 1 by 2 pi root of G by L. So as you increase the length of the pendulum, the time period will increase, but the frequency will decrease. Okay, how many cycles it is making in 1 second is going to be less. Okay, so let's see what else I can do here. So again and again, we are going to use this concept called restoring torque or restoring force. So what is the force which is going to bring it back? Or what is the torque which is going to bring it back? Okay, if it is force, it is going to be linear world. If it is torque, it's going to be rotational world. Let me open the textbook. So I think Some of the topics, whatever is there, we'll discuss that alone. Okay, carefully listen. Let's see what are the things which you have completed. So introduction, okay, you can read through it. Periodic and oscillatory motions. They are given a lot of other derivations, which is not required in this particular chapter. Period and frequency, you know what it is. So these are all theories only, you can read through it, nothing very difficult. So, frequency, we talked about this pendulum. A cos omega t, right? We talked about it. 2 pi by omega. Okay, I think this is coming later. We will discuss this later. In this plot, the curve V has half the period and twice the frequency of curve A. Okay. So they're trying to discuss different. We talked about this one, uniform circular motion versus simple harmonic motion, right? These things, I don't think we discussed it, but I don't know how they can ask these kind of questions. We'll come back and I'll take a look at it. This one I already discussed this, right? So I showed it like a shadow thing. Yeah, it's the same thing, shadow thing, omega t. So you can have a starting point. So phi has to be added. So velocity and acceleration, simple harmonic motion, we already discussed it, right? So differentiating this, we discussed this, omega squared into x is the acceleration, negative of the displacement. So whatever given, I think it will cover most of the things. Okay, some of the topics it's not covering, so we'll talk about that. I discussed this one. Using f is equal to kx versus f is equal to ma, right? I can calculate omega like this. So it will be like omega is equal to square root of k by m. Okay, this needs to be added in the handbook. F is equal to ma, f is equal to k x. Ma can be written as m omega squared x, right? So it means if I equate this and this, I'll be getting omega is equal to square root of k by m. Okay, if you equate this and this, you'll be getting this one. Energy in simple harmonic motion, we discussed this. Go back and check in the last class. Half kx square, we talked about it. We talked about these two curves, right? We talked about these derivations, half k squared. How did I get half m omega squared? K was replaced with m omega squared. Okay, just from the formula which we studied right now. Omega is equal to square root of k by m. Okay, so this one. Omega is equal to square root of k by m. So if I square it on both sides, I'll be getting k is equal to m omega square. So oscillations due to a spring, we need to discuss this. I think this is what we discussed right now, mg cos theta, mg sin theta, right? We talked about all these derivations right now. Okay, tau is equal to I alpha. So go back and study it. Damped simple harmonic motion, we talked about it, right? So I showed you this diagram, surrounding medium. This is damped oscillation. This is BV. We talked about this. This is a vector. This is also a vector. So capital letter means vectors. Forced oscillations and resonance. This is the derivation which I talked about. Okay, right now. So go through this textbook. Okay. I talked about the special cases of omega d into b. Why? Because it's coming from this formula. Suppose if it's resonance, what will happen is this and this will cancel. So what is left is omega d square b square root. So square root and these two squares will cancel. So that's why you are getting f naught is equal to omega db. Naught is equal to omega d by b. Sorry, omega d. Amplitude is equal to f naught by omega db. In my opinion, they are given so much of mathematics which you don't have proper background. This experiment, we have it in the lab. I'll show you this. Okay, so what happened to the other systems? Okay, I thought they have, I wonder if they have removed some of the syllabus. Oh, okay, I think it's given in the additional exercise. Definitely not an easy chapter, okay, unless you take some effort. This is going to be a difficult chapter. So my PDF is causing a lot of trouble. So we'll talk about these additional exercises in the next class. Okay, with that, I think this chapter will be over. So this one I need to discuss, and then I need to discuss this one. Piece of car oscillating. And then anything else, if that is remaining, we'll discuss that. Okay, so it's already late. So I have three more, at least 2 or 3 derivations that needs to be discussed in the next class. Okay. So your homework is to study whatever I completed in the handbook. So page number 37. You need to study all these things, whatever I completed up to this point. These things are not done. And then I did this first block in the next page. Okay. So that's your homework. So most probably next class I'll be completing. Today is Friday, is that right? So Monday I'll be completing these derivations, 2 or 3 derivations, and then either I'll be giving you a test or I'll be doing the numericals. How is it going in your schools? Do you want more help in the theory or do you want more help in the numerical? If you give me a proper feedback, I can do accordingly.
So numericals.
Numericals?
Yes.
You need more help in numericals.
Yes.
Is that right? Okay.
Yes.
What about
Yes.
the theory?
So theory we can study by ourselves, sir, but numericals.
Study by yourself. Okay. That sounds very different to me. Because some of the theories, definitely you will need some help. Okay. I'm sure you cannot do it without teaching in the class. Okay. So numericals, of course, the derivations which I was showing you, it is coming in the numericals. It is coming in the additional exercise. So we'll do some of the things there. Again, I may not have time for the entire numericals to do. So maybe I'll do some maximum, say 5 to 10 problems. Okay, so the remaining you should try it. So then we'll discuss. If you have any doubts, we'll discuss it. Okay, thank you all. Bye. If you have any doubts, stay back. Otherwise, you are free to go. Thanks.
Thank you, sir. Bye, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.